Hello everyone, welcome to part 11 module 6 data communication. So in part 10 we discussed the basic idea about this spread spectrum concept, and hope you got an idea how this spread spectrum is working in general. Now we move on to the particular category, the first category of spread spectrum encoding technique called the frequency hopping spread spectrum, and we will see how it is working here. So with frequency hopping spread spectrum, the signal is broadcast over a seemingly random series of radio frequencies hopping from frequency to frequency at fixed intervals. So we will see with an example. I will explain how it is working. So right now you understand, like we have a signal that is to be communicated. Normally we will be sending this signal with respect to a single frequency, right? The signal will be centered on a particular frequency and we will be transmitting. But what makes it different is, instead of sending the signal using a single frequency, we will be broadcasting or spreading that signal over a number of frequency. Okay, so that what makes it then means that confidentiality means other some benefits we already seen for that spread spectrum, right? We are achieving all those benefits by means of spreading the input over a number of frequencies. Now on the same way, the receiver has to be tuned with the spreading code, so that how the sender is spreading the information, in that way the receiver can de-spread the information back. So at a receiver hopping between the frequencies in synchronization with the transmitter. So how the transmitter is sending when we have a set of frequencies, to what frequency the transmitter is sending that information at a particular moment point of time, to the same frequency the receiver has to be tuned. So there should be some kind of synchronization between the sender and the receiver, or that spreading code should be communicated between them. And if it is communicated prior to actual communication, then the receiver can tune with the same frequency, so that and he will pick up the message. So I would be eavesdroppers here only unintelligible intelligible blips, in the sense, if somebody is trying to eavesdrop your information, some kind of some third party is trying to listen to your conversation, and he may be tuning with a particular frequency, but immediately you are switching to some different frequency, so that even though he tried to eavesdrop your communication, he will be getting only a very small number of bits of your communication, because without the eavesdropper's knowledge you are just hopping to a different frequency, right? So you have that means benefit here. So that what makes it very suitable for the wireless communication, because the chances of eavesdropping is very very high when it comes to wireless communication than the wired communication. So when you switch from one frequency to another frequency, even though the eavesdropper tuned a particular frequency and he will try to listen to that frequency, immediately you are switching to a different frequency, so that rest of the information he will not be getting, and he can't predict what is the information being transmitted. So the attempts to jam the signal on one frequency succeed only at knocking out a few bits of it. Similarly, if the attacker tries to jam the signal at a particular he's actually trying to jam the signal and he tuned a particular frequency, he applied that signal jamming, but immediately you are switching to different frequency, so that only few bits is getting affected because of it. So it is not a big problem now. So it is like this. With this figure, let's try to understand how the concept is working. Here we have a this frequency energy diagram, some kind of channel assignment. So what is happening is, this is the frequency 1 that is allocated for a particular in normal communication, every signal will be allotted a particular frequency. For example, this is a frequency allotted for a particular communication, and let F2 be the frequency that is allocated for some other pair of communication, and F3 is another pair of communication. For example, let it be like that, and we have some what called 8 different such frequencies. Okay, now the thing is that so even though here this numbering and all is given, and that is something different. So right now you assume like that. Okay, so that is a normal scenario. We will be using a single frequency. Now what is going to happen? The sender want to communicate some information, and this is a range of frequencies over which he is going to spread the information. Okay, as of now this is just shown only here. Don't think like so 8 different pairs of transmitter and receiver are communicating. It may happen also when it comes to sharing of the information. As of now you assume that we have just a single transmitter and a receiver, and they are communicating. Instead of using a single frequency, instead of communicating that information centered on a particular frequency, now they have a choice, like 8 different frequencies are available to them. Now what they will do is, first they will tune to frequency 5. Okay, so so if you are looking at the time frequency diagram, during the first interval of time, the small units of time, the information is sent through frequency 5. Okay, and in the next portion of the time, interval of time, now it is tuned into frequency 8. Okay, so that assignment is shown here. Okay, frequency 8, and then it is tuned to frequency 3. So you can see that the part of the information being sent over frequency 3 over the third slot of the time. Then it is tuning to frequency 6. Okay, so this is our spreading code actually. So this spreading code will be communicated to the receiver in advance, so that only and no one else is knowing this spreading code, only the sender and receiver are knowing this. So what the receiver can do now is he will also tune in the same way, like during the first interval of time he will tune to frequency 5, so that he will get the first part of the information being sent by the sender. Now in the second interval of time he will tune to frequency 8, so that he will get the subsequent, the following part of the information. Like that he will get the entire information in order. Okay, the only thing is this is the spreading code, and that is to be communicated with the receiver also. Now how this spreading code, or who is deciding this pattern, and that is purely random, so that make it different. Like nobody can predict this sequence. Like now I am sending through frequency 5, next I am sending to say frequency 8. Now in the third slot, to which frequency I am going to send the information, that no one can predict. In that way you have to generate the pattern. Okay, so that makes it different. Now this, using a pseudo random number generator, you can generate this sequence. So that is the idea. And the same pseudo random number will be used at the random number generator will be used at the receiver side also. Same pseudo random number generator in the same algorithm, and the initial seed value will be known to the receiver, so that the receiver will also generate the same pseudo random number sequence, so that he can tune with the same frequency, and the communication will happen in a synchronized way, so without any problem. Now this is frequency hopping spread spectrum. So we are spreading our information over a range of frequency, and that range of frequency, that pattern is being generated by the pseudo random number generator. Now you will be thinking like during the initial slot of time we are using frequency 5. Now you can think of it like here it is showing just a communication between a pair of devices only. Now you can multiplex this same range of frequency for a different pair also, or maybe any number of pairs, because once the frequency 5 is allocated to this the current pair which we are discussing for the first interval of time. Now in the next interval of time, actually frequency 8 is being utilized, 5 is now free. Now you can efficiently have a multiplexing algorithm by which you can allot this frequency 5 to the different pair, because it is free now, right? The same thing is applicable to other frequencies also. In that way you can use it for multiplexing also. And anyway, this multiplexing concept we will see with respect to the next category, like direct sequence spectrum. From that we will move on to that. We will give you try to give you an idea about how this multiplexing is happening. Anyway, right now I hope you got an idea. So what we are actually, the multiplexing, what we are trying to achieve is Means we want to utilize the frequencies fully. Here the utilization for this frequency 5 or the channel with frequency 5 is only for the first duration of the time. After that it is free, so definitely you can give it to a different pair of sender and receiver, and after that you can give to a third pair, like that. So in that way you can enable the sharing. And when we are sending like this, we are getting that benefit of then some interception, jamming, those kind of eavesdropping, those kind of attacks are not possible, and confidentiality is there, of course, because as attacker is not able to get your information, right? When he is tuned into frequency 5, immediately you are switching to frequency 8, and that the attacker can't even predict to which frequency you are going to. Only the sender and receiver will be knowing, because we are generating that sequence in a purely random manner. So this is just a small example with 8 different frequency, and for more performance or efficiency, you can think of spreading the information over some bigger range of frequency. As the range of frequency is more and more, that much efficiency you are getting, but you should be able to utilize the resources well also, because wastage of resource should not be there. Okay. So the figure shows an example of a frequency hopping signal. A number of channels are allocated for the frequency hopping signal. Typically some 2 power k carrier frequency forming 2 power k channels in our example. 2 power 3, like that, 8 channels we saw. Why this 2 power k? Because we will see, we are using some kind of frequency, since it's a table, and to that table, this k bit will be acting as an address, and from that you will be selecting a particular frequency, and that will be allotted in that way. So that calculation and all will be easy if you are making it some power of 2, that's all. So the spacing between the carrier frequency and hence width of each channel usually corresponds to the bandwidth of the input signal. I mean, what is the width of that interval? The transmitter operates in one channel at a time for fixed interval. For example, IEEE 802 standard uses 300 millisecond interval. So that is the width of the time for a particular frequency, just like we see in the previous diagram. First it chooses frequency 5. How long it will be using frequency 5? Say 300 millisecond of time. So that is a particular value that is being used in IEEE 802.11 standard. It may be different. They have their own criteria for fixing this interval, everything. Now during that interval, some number of bits is transmitted using some encoding scheme. Now a spreading code dictates a sequence of channels to be used, like what we seen at the top, that is a spreading code. Now both the transmitter and the receiver use the same code to tune into a sequence of channels in synchronization. So if you are looking at diagrammatic view, how the things are happening, the block diagram kind of thing, the binary data is coming. It can be analog data or digital data, like what we already seen. If it is digital data like binary data, then you can use a digital to analog modulator, I mean converter and encoder, in that way, in any way you can call, right? When it comes to digital to analog encoding, that is all called the modulation. Those things we already seen. We can use techniques like frequency shift keying or binary phase shift keying or some other digital to analog conversion technique, and that will be generating the analog signal. So we need the analog signal as input to our frequency hopping spreader that we already seen. And now the pseudo noise bit source or the pseudo random number generator, okay, or the pseudo noise generator, we are using different terminology for this, and that will generate a number, okay, like 1 2 3 4. In the previous case, initially it generates the number say 5 something, that frequency it will randomly generate. So once it that generate that number, so in that previous example you can think of it as a 3-bit number. Say it is generating the 3-bit number, say 101. Okay, now it will be looking at the channel table and it will see what is the frequency corresponding to that 101 location, that is frequency 5 or whatever it is, and that will be given to a frequency synthesizer will be generating the equivalent frequency for the generator random number. Okay, that's also this random number generator will be just generating a number, and that corresponding to that number a particular frequency will be generated by the frequency synthesizer. Now the frequency hopping spreader is what he is doing. The input signal will be having some reference, some central frequency, right, and to that central frequency this will be added. So that means you can assume like the center frequency is say some reference value. If it is say 0, I am just taking, then if it is generating some 5, 0 plus 5 like that, or if it is some 100, then 100 plus 5. So with respect to the reference frequency of the input signal, this value will be added up. And at the receiver side, the same way this added value will be coming, and this same frequency will be generated, and that will be subtracted back, so that he will be getting the original signal back. So this sum frequency will be given to a band pass filter, and it will correctly generate the signal centered on that particular frequency. So that is the idea, and this will be our spread spectrum signal. Now at the receiver side, this spread spectrum signal will be coming, and the frequency hopping de-spreader will be working at the receiver side. The same pseudo random number generator will be generating that binary, and that just an index to the table from which we are generating the frequency channel table, and the frequency synthesizer will be generating the equivalent frequency out of it. And now the actually what we are getting is a sum frequency, right? From that you have to subtract and take that difference frequency, and using the band filter you will be getting the original analogous signal centered on the reference frequency. Okay. Now the demodulator will be converting it back to the the same FSK or PSK we will apply in the reverse order to generate the binary data. So everything is working fine. So this is the diagrammatic view, just an explanation for that. A typical block diagram for a frequency hopping system is shown in the figure. For transmission, the binary data are fed into the modulator using some digital to analog encoding scheme, such as a frequency shift keying or binary phase shift keying. The resulting signal is centered on some base frequency. That is that is what I called as a reference frequency. Some base frequency will be then the pseudo noise or the pseudo random number generator using that. It serves as an index into a table of frequency. Okay, that is the channel table, and this is the spreading called referred to previously. Now each key bit of the pseudo noise source specifies one of the 2 power k carrier frequency. At each successive interval, a new carrier frequency is being selected in that way, and this frequency is then modulated by the signal produced from the initial modulator to produce a new signal with the same shape, but now centered on the selected carrier frequency. Now on reception, the spread spectrum signal is demodulated using the same sequence of pseudo number derived frequencies, and then demodulated to produce the output data. And the same way, just an explanation on the figure. I already explained using that figure, right? So in the exam, if they are asking that frequency hopping, you can just simply explain like and just try to give those diagrams so that it is very clear for the evaluator to evaluate your answer sheet. Okay, so that about frequency hopping spread spectrum. And now we will see another variant of this spread spectrum concept, the direct sequence spread spectrum, in the next part. Thank you.